When we think of the word technology, our minds immediately drift to silicon chips, steel skyscrapers, and the hum of electricity. We have been conditioned to believe that complexity requires industrialization, and that sophistication is measured by the height of our buildings or the speed of our engines. But there is another kind of technology. A technology that does not fight against nature, but masters the physics of it. A technology born not in factories, but in the quiet observation of the world over thousands of years. Before the first steel mill was fired, the indigenous peoples of North America were already masters of chemistry, structural engineering, aerodynamics, and thermodynamics. They did not just survive on this continent, they engineered it. They solved the problems of shelter, transport, and tools with a brilliance that modern science is only just beginning to fully understand. This is not a story about primitive survival. This is a story about advanced innovation. Today, we are going to deconstruct the genius of the first Americans. We will look at how they turned raw stone into blades sharper than surgical steel. We will analyze the chemistry they used to turn rotting skin into waterproof velvet. We will examine the mathematics woven into their baskets and the physics built into their boats. We are going to explore the skills and crafts of the Native American tribes not as museum artifacts, but as triumphs of human engineering. To understand this genius, we must look at the four elements that formed the foundation of their material world: stone, wood, hide, and fiber. In each of these categories, Native American craftsmen achieved a level of mastery that rivals anything produced by modern machinery. Our journey begins with the earth itself. Stone. For most of us, a rock is just an obstacle in the ground, but to a master flint knapper, a stone is potential energy waiting to be released. The indigenous peoples of the Americas, from the volcanic regions of the West to the flint-rich valleys of the East, mastered the physics of what geologists call conchoidal fracture. This is the understanding that certain stones, like obsidian, chert, and jasper, do not break randomly. When struck with precise force at a specific angle, usually less than 90 degrees, the force travels through the stone in a predictable wave, peeling off a flake that is incredibly sharp. This is not banging rocks together. This is controlled shockwave mechanics. The most famous example of this engineering is the Clovis point, a specific type of projectile point created over 13,000 years ago. These points were fluted, meaning a long channel was chipped out of the base to allow it to be hafted securely onto a spear shaft. This design was so successful, so aerodynamically perfect, that it spread across the entire continent. But the pinnacle of stone technology is found in obsidian. Obsidian is volcanic glass. When a master knapper strikes a flake from a core of obsidian, the edge that is created is thinner than a molecule. To put this into perspective, the finest steel surgical scalpels used in modern hospitals have a jagged edge when viewed under a microscope. They tear the flesh as much as they cut it. But an obsidian blade created by a Native American craftsman is smoothed down to the molecular level. It separates cells rather than tearing them. This is why some modern surgeons have experimented with using obsidian blades for delicate operations, realizing that the Stone Age technology actually produced a sharper edge than the Industrial Age. But creating these tools required immense skill. The craftsman had to understand the grain of the stone, the velocity of the strike, and the density of the tool he was using. He would use a hard hammerstone for the initial shaping, removing large flakes to thin the piece. Then he would switch to a softer tool, often an antler billet from a deer or elk. The antler is softer than the stone, which allows it to bite into the edge and pull off long, thin flakes that travel across the face of the blade. The final stage of this engineering process is called pressure flaking. This is where the sheer brute force of the hammerstone is replaced by the delicate, calculated pressure of the hand. Using the tip of a deer antler or a copper tool, the The napper pushes against the edge of the stone, popping off tiny, microscopic flakes to sharpen and serrate the edge. This allows for incredible precision. Points could be made with notches for binding, with serrated edges for cutting through hide, or with specific aerodynamic profiles for flight. This was not a crude process. It was a reductive sculpture that required a three-dimensional understanding of geometry. While stone provided the cutting edge, wood provided the structure of civilization. And nowhere was the mastery of wood more evident than in the Pacific Northwest and the Great Lakes regions. In the Northwest, among tribes like the Haida, Tlingit, and Coast Salish, the Western Red Cedar was known as the Tree of Life. These people were the supreme engineers of wood. They didn't just cut lumber, they harvested planks from living trees without killing them, a sustainable forestry practice that ensured resources for future generations. But their greatest engineering feat was the ocean-going canoe. These were not small riverboats. These were massive vessels, some over 60 feet long, carved from a single cedar log. They could carry dozens of warriors and tons of cargo. But the engineering challenge was significant. A single log is round and tippy. How do you make it stable in the rough waves of the Pacific Ocean? The answer was steam technology. After carving the hull to a specific thickness, often measuring it by feel or by drilling small holes to check depth, they would fill the canoe with water and drop in red-hot rocks. As the water boiled, the steam and heat penetrated the cellular structure of the cedar wood, softening the linen that holds the fibers together. Once the wood was pliable, the craftsman would gently insert crossbeams, pushing the sides of the canoe outward. This process, known as spreading, did two things. First, it made the canoe wider than the original tree it came from, increasing its stability and cargo capacity. Second, and more importantly, it introduced tension into the hull. As the wood cooled and dried, it tried to shrink back to its original shape, but was held in place by the thwarts. This created a pre-tensioned structure, similar to how modern concrete is pre-stressed. This tension made the hull incredibly rigid and strong, able to withstand the pounding of ocean swells without cracking. On the other side of the continent, the Anishinaabe and Algonquin peoples faced a different problem. They lived in a land of millions of lakes and dense forests. They needed a boat that was light enough to be carried over land between rivers, yet strong enough to carry heavy loads of fur and meat. A heavy dugout canoe was useless here. So, they engineered the birch bark canoe. This was a marvel of composite material engineering. It used specific materials for specific stress loads. The frame was made of cedar, which is light and flexible. The skin was made of birch bark, which is waterproof, rot-resistant, and incredibly tough. The binding that held it all together was made from the roots of the spruce tree, which are stronger and more pliable than rope. And finally, the waterproofing was a mixture of pine pitch and charcoal, a natural epoxy that sealed every seam. The genius of the birch bark canoe was its flexibility. Unlike a rigid wooden boat that might crack when hitting a submerged rock, the birch bark canoe could flex and absorb the impact. It was the ultimate all-terrain vehicle of the ancient world. For the tribes of the Great Plains, the Lakota, the Cheyenne, the Arapaho, the Comanche, the primary material resource was not wood or stone, but the animal itself, specifically the buffalo. But utilizing animal skin presents a major chemical problem. Raw skin is roughly 80% water. When it dries, the protein fibers glue themselves together, turning the skin into rawhide, a material hard as wood and useless for clothing. If it stays wet, it rots. To turn raw skin into soft, wearable buckskin, you must perform a chemical transformation known as tanning. European tanners used vegetable tannins from tree bark, a process that took months. The Native Americans, however, used a different chemical agent, one that was readily available in the animal itself, the brain. Every animal, whether a buffalo or a deer, has a brain that contains exactly enough emulsified fats and lipids to tan its own hide. This is a perfect example of the indigenous philosophy of efficiency and waste nothing. The process of brain tanning is grueling physical labor combined with organic chemistry. First, the hide must be fleshed, scraping away every bit of meat and fat. Then, the hair must be removed. The chemical step involves cooking the animal's brain in water to create a slurry, which is then rubbed vigorously into the hide. The goal is to coat the collagen fibers of the skin with these brain fats. But the application is not enough. The water must be evaporated out while the oils stay in. This leads to the most exhausting step: softening. The hide must be stretched, pulled, and worked back and forth over a rough rope or a wooden stake constantly while it dries. If you stop for even a few minutes, the fibers will lock together and the hide will stiffen. The friction of the stretching generates heat, helping the oils penetrate deep into the cellular structure. The final result is buckskin, a material that is soft, breathable, and durable. But the Plains tribes didn't just want soft leather. They also needed hard plastic. By manipulating the drying process, they created parfleche. This is rawhide that has been cleaned and stretched, but not broken or softened. It dries into a material as hard as plywood. The Plains tribes folded this material while it was damp into envelopes and boxes, which then dried into rigid, waterproof suitcases used to transport dried meat and tools across the prairies. Even more impressive was the engineering of the war shield. Using the thick hide from a buffalo's neck, they would shrink it using heat, condensing the fibers until the hide became incredibly dense. A properly made Comanche or Lakota shield could stop a flint arrow and even deflect a low-velocity musket ball. This was the Kevlar of the 18th century. Whether creating the softest cradleboard cover for a baby or the hardest shield for a warrior, the mastery of hide was a testament to their understanding of material science. Perhaps the most underestimated of all indigenous technologies is basketry. We tend to think of baskets as simple containers for holding fruit. But for tribes like the Pomo, Hupa, and Yurok of California, baskets were high-technology appliances. They didn't use pottery because they traveled frequently, and pottery is heavy and fragile. Instead, they engineered baskets that were watertight. This seems impossible. A woven object holding liquid. But through a deep understanding of plant fibers and fractal mathematics, they achieved it. The Pomo weavers are widely considered the greatest basket makers in human history. To make a basket watertight, the weaver used a technique called coiling. The stitches were so tight, sometimes 40 to 60 stitches per inch, that when the plant fibers became wet, they would swell, closing the microscopic gaps between them and creating a waterproof seal. But the engineering didn't stop at storage. They used these baskets for cooking. Since you cannot put a woven basket over a fire, they brought the fire to the basket. This technique is called stone boiling. The cook would heat volcanic rocks in a fire until they were glowing red, then drop them directly into the basket filled with water and acorn soup. The heat transfer was immediate, boiling the water in seconds. This required a basket that was not only watertight, but tough enough to withstand the thermal shock of hot rocks and the abrasion of stirring. In the Southwest, the Din, known as the Navajo, took weaving to a different level with their famous rugs and blankets. This was not just craft, it was algebra in motion. A weaver would sit at her upright loom and visualize a complex, multi-bordered, geometric pattern. She did not draw it on paper first. She did not calculate the thread counts with a calculator. She held the entire algorithm of the design in her mind, adjusting the tension and the count of the warp and weft threads row by row. If she miscalculated by a single thread early in the process, the entire pattern would be misaligned weeks later. The mental acuity required for this is staggering. Stone. wood, hide, fiber. These were the 4 pillars of indigenous engineering. To the untrained eye, a birch bark canoe or a willow basket might look like a simple object. But when we strip away our modern biases, we see them for what they truly are, the result of thousands of years of research and development. They are the perfected solutions to the problems of survival. The Native American peoples did not live in a primitive state. They lived in a state of high adaptation. They possessed a deep scientific literacy of their environment that allowed them to thrive in the freezing Arctic, the scorching deserts, and the dense woodlands. Today, many of these skills are being revived by a new generation of indigenous artists and engineers who understand that the old ways are not just history, they are the future. They teach us that true technology is not about conquering the earth, but about partnering with it. So the next time you hold a piece of manufactured plastic, remember the hands that could turn a rock into a razor and a tree into a traveler. Remember the forgotten genius of the first Americans. Their legacy is not buried in the ground, it is woven into the very fabric of this continent.